So the equilibrium constant K, it's important. The equilibrium constant and the expression for the equilibrium constant are for the chemical equation as written. You can have completely valid reaction constants that describe the same physical situation, but they will look different if the underlying reaction is written down differently. For example, let's say we're looking at the reaction of nitrogen and hydrogen to make ammonia. And so in this case, the equilibrium reaction is, we don't know the equilibrium constant. We know its value, but we do know how it should be written. It should be written as a product, NH3 squared over reactant, and concentration of reactants. And here we have H2, and this is to the third. So that's going to be the equilibrium constant for that reaction. Now let's look at the reverse reaction. Ammonia decomposing into nitrogen and ammonia and hydrogen. So here we have a Kc is equal to, will be H2 to the third N2 divided by NH3 squared, right? It's the same chemical content, except now it's a decomposition. So we write down the equilibrium constant for the reaction as it's stated. Notice in this case that let's call this K forward and this K reverse. The K forward equals 1 over K reverse and vice versa. So it's the same physical information that's contained here, but if we write down a different reaction, we'll get a different reaction coefficient. A different reaction constant. Let's take a look at this reaction. Now this is essentially the same reaction as the first one, but we've doubled all the stoichiometric coefficients. So the Kc here is going to be the concentration of products to the fourth N2 squared times H2 to the sixth. So this case, this Kc is equal to Kc or a K forward squared. But for this chemical reaction, that is the right Kc, and they both contain the same amount of physical information. If you were to work through a problem where you're relating actual concentrations to the equilibrium constant, you would get the same physical answer in the end. So it's fine to use whatever chemical equation you use, as long as you're always consistent. If you are, you might be able to write different equilibrium constant expressions that will give you different equilibrium constants. But when you plug it into a physical problem, as long as you always use the same equation, you're going to get the same physical answer. They're just different ways of writing the same the physical content. So when you look up an equilibrium constant, you always have to ask, wait a minute, which equation is this for? Because if you don't specify the equation, you don't actually know physically what that equilibrium constant means. Okay. So what are the units of the equilibrium constant? This is something that's really important because this is an example, this is a interesting quantity that actually doesn't have units. There aren't any units in this. You might think, oh, well, it's going to have concentration. It's going to have concentration. This is molar. This must be molar squared divided by molar times molar to the third. So it must have concentration molar to the -2, but it doesn't. And that is because the equilibrium constant is actually defined as the concentration of ammonia divided by the standard state. So NH3, whatever the concentration is, divided by 1 molar, because that's the standard state in concentrations. Same thing here. It's the concentration of nitrogen divided by 1 molar, concentration of hydrogen divided by 1 molar, and then that cubed. So it's actually a relationship that has no units. Yeah, why 1 molar? It's because Kcs are defined in terms of the standard state. If you change the standard state, you will change the equilibrium constant because you're changing the reference for what it means to be 0 energy or higher energy or lower energy. So that's important that when you look at the KCs, you not only have to know the chemical equation, you have to know the standard state. If you don't know the different standard states, if I decided to make my standard state 100 degrees instead of 25 degrees, the equilibrium constants would change. And so, or instead of 1 molar, 0.1 molar, then they'd change as well. So that's also important to know. So just so you know, when we start taking, exponential logarithms of equilibrium constants, this is why, they actually are unitless expressions. Let's do some examples as well. So we've got a mixture of carbon monoxide, hydrogen, and methanol at equilibrium. The balanced chemical equation is carbon monoxide plus 2H2 goes to methanol. At 250 degrees C, the mixture is equilibrium now and contains these concentrations. What's the value for Kc? Well, this is pretty straightforward to figure out because all we need to do is write out the expression, concentration of methanol divided by concentration of carbon monoxide times concentration of hydrogen squared. So that'll just be 0.150, not molar because it's really the concentrations divided by the standard state, which is 1 molar, for 1 molar for when we're measuring things in concentrations, 0.0960, and then 0.191 squared, and that gives 42.8. So that will be the equilibrium constant at this particular temperature. At a different temperature, the equilibrium constant